I am assistant professor at Bursa Technical University in Turkey. And Bursa Technical University has a great opportunity because we are really near located near to one of the biggest furniture manufacturing cluster in Turkey. That's why we always touch each other, and university and industry touch each other. Today I will talk about the application of probabilistic approach, and what is the probabilistic approach. I will talk about it, and one example I will show you, and using this application, this approach, how to design a reliable furniture. And basically I will give some examples from sample data, and then we will look at how we measure the reliability of joint or reliability of all construction. In today's lecture, today I will talk about what is reliability, and then why reliability is important for us. And then I will talk about the fundamental probability theory because it is important for us to understand probabilistic approach or the reliability analysis. And then I will give, in this part, I will give one example based on the side chair frames, and then we jump to multiple failure modes. And in this one, we will talk about the really for one joint reliability and all construction reliability together. And then I will talk about the probabilistic approach, and I will explain one of them. There is lots of several probabilistic approach techniques, and I will touch one of them, which is tolerance analysis. And then lastly, we will talk about the predictive failure analysis, and in this one, we will measure we will see how to measure lifetime or cycling time or fatigue life of the one chair or one furniture construction. So I try to explain every calculation in a very simple way because I make some assumption. That's why they may adaptable for any other example of the furniture construction. So let's start. First, I will talk about what is reliability. Reliability is defined as the overall consistency of a measure. So if we talk about the reliability, and if we say one product is reliable, so every time this product gives this same service or the same results in every application, so we can call it reliable. So for furniture construction, what is reliability? How to measure reliability of furniture? So, and that one, so furniture makes for human and pets together. So we are the user of that product. So it should be served to human and pets. And in usage purposes, it should be reliable. And if we sitting furniture group, if you are talking about the sitting furniture group like a chair, so it's proposed when we sit down or lean back, it should be reliable. Or if we talk about the bookcase, when we put our books, the bookcase shelves must carry the weight of that book. So firstly, in reliability analysis or tolerance analysis or probabilistic approach, we need to first define what type of construction we are using, and then what is the user. Which one is user? Human or objects or pets? So after that, we can start our analysis. So that's why if we talk about the human, so we are in different age, different sex, or different type of body type. And that's why in every single chair, for example, chair construction, we apply a load, but in different level. Or a same person during a day, he or she may have different sitting position. So we apply different load again. Our load level is changed. Or also different objects. If you are talking about a bookcase or TV stand, so there is a different load for this type of furniture. So how we get same result every time in the in every application? For this one, we are using a data set and probability. So I will show you a quick graphic for this one. So I will explain the terminology in here. But first, I need to get, but I cannot get it. So I would like to check the laser point from here. So I didn't get it.
But we can see see your mouse, so
yeah,
it's fine.
We can work this way. So if we're talking about the probability, so probability of failure in the shaded area. So in every time, if we apply a load on the chair frame, this load should be in this area, in the white area. We call this load distribution. And also we have a capacity distribution. This capacity distribution should be construction itself strength, or material strength, or joint strength together. Which one we define? We apply to we apply load to this material or joint or the construction. So if we pass this shaded area, failure starts. But what is the failure rate? We need to measure it. So the capacity distribution is material strength, joint strength, or strength of the furniture construction itself. So we can measure this one from the laboratory test. The joint strength or the construction strength, we can measure it. So also we apply some loads on it, and how we damage this area. We can measure how we can damage this area. So for this one, we need to use probability. So that the area of the what is the area of this shaded section? This gives us the failure rate. So, and then we can calculate the reliability. So load distribution is the applied load on materials, joint, or furniture construction during service. So this service should be in laboratory test or in real life. It doesn't matter. So it will change how we can collect the data. And the probability of failure is the area of the compensation of applied load on this whatever is joint or furniture itself or just material and their capacity. For this one, we can just jump to some basic phenomena. In our title, we talk about the probabilistic approach. And also there is two approaches. One is the deterministic approach, the second one, probabilistic approach. Deterministic approach are more conservative than the probabilistic approach. For example, point estimation. If we give a mean and standard deviation of data set, and we can get a single estimate from this data, is the point estimation. Also, we can use safety factor for example, in civil engineering department, also in furniture construction, in strength design of the furniture, we can use this safety factor. It should be just 1/3 of the maximum strength or 20% of the modulus of rupture. We can use that, but they are still deterministic approach. They estimate only one variable or one result. Or we can use worst case scenario. We just think about that. What is our worst case? And we apply to this scenario to our furniture. So, for example, we just choose the heaviest person in the population and measure, and we can get just the people in laboratory. He can or she can sit the chair, and we can test our reliability of the chair. Is broken or not? What is the worst case scenario? What is more conservative? Which one is our worst case scenario in our usage purpose for this furniture construction? And also there is another technique. It's out of the deterministic approach. We call it Six Sigma. But the Six Sigma gives us with really high reliability. The failure rate is almost 4 in 1 million. But it must be too much respectful for us. It's too high for us. Maybe we can not reach this reliability in practical application. That's why we need to choose a failure rate for our construction and our furniture manufacturing strategy. We can choose the reliability level for us. So if you are making quality, better quality furniture, you can hire reliable, or low quality and you give a cheap price for it, you can reduce your reliability level and just put your chair into the market with the cheap price. This preference is based on your manufacturing strategy. But other way, we can talk about we can test that material or joint or furniture construction itself. Measuring a reliability is not easy in that much, because especially in the wood material, there is so much uncertainties. These uncertainties are loading. During time, how many people can use a chair? We cannot know that. How many cycles is applied on that chair? We can know that. We can not know that. Or also material properties. If it is talking about the wood furniture, our material is orthotropic material. Or also, if one member comes from the members comes from the same trunk from the tree, so the materials or parts should come from softwood or hardwood. So their mechanical property is different. Or geometric size, or manufacturing tolerances. In manufacturing tolerances, when sample size or production scale with the increasing with production scale, our manufacturing errors is increasing. So we can start to produce different level products, but under the lower and higher tolerances. But every time they are not giving the same results. There is a difference between them. So if we go to the large scale production, the manufacturing tolerances or manufacturing errors is increasing, and also time is one of our uncertainties. Over this terminology, how we can set up our reliability of the product, which one we can use? The answer is the probabilistic approach. We should use probabilistic approach. It gives us a better or reliable results rather than the deterministic approach. Deterministic approach is not useful. We can use it, but if we talk about any uncertainties or variability in our data set, probabilistic approach will give us a better understanding to set up the reliability. And I will talk about the probabilistic approach later on this presentation. And just a little bit, I will talk about what type probabilistic approach we have. So the probabilistic approach, Monte Carlo simulation, first order reliability method, the second order reliability method, impostance sampling, the response surface methods are the probabilistic approach. If we go down, it is getting more complicated. If we go up here, so the Monte Carlo simulation is really easy to apply. But if you go to down here, so application method or the complexity is getting more higher. Today we will talk about another probabilistic approach, which is tolerance analysis. So later I will talk about the tolerance analysis in this presentation. So let's jump to why is reliability important. Because reliability is a concern of furniture producers for sustainability, human safety, and global marketing, competitive marketing, as furniture quality and reliability increase chances for higher market success. So, if we have reliable furniture, it's going to be sustainable because we can increase its lifespan. We can increase chance of its reusability or remanufacturability. And also, if it's reliable, we can save the human. So because of the furniture accidents, many people have fatal injuries. And also, if your product reliable, you will have higher market chance you have a higher chance in your competitive marketing to sell your product. So let's touch a little bit sustainability, human safety, and the global competitive marketing a little bit. So the sustainable products aims for reduction of its environmental impacts while increasing its lifespan. So if we can reliable furniture, a durable furniture, we can increase its lifespan. So in here, we just use in the usage part, and that one, if we use reliable furniture, if service life it's done for me and I can sell it, it can be reusable. So I cannot send it to retirement or the disposal. Another person can use it. If it is not reliable, in the first service life, in the first user, if it's broken, and the user cannot know what is the reliability, what is the environmental impact of the furniture or the recyclability of the furniture, he may just throw away, and the furniture goes to the disposal. So it is our problem. If we increase the lifespan of the furniture, and by increasing its reliability, we can have this sustainability. So increase product life cycle, increasing durability, reliability, and remanufacturability in terms of design for environment strategies. If we talk about the design for environment, we just talk about the green furniture and biocomposite material, and green material, eco-friendly material, or during transportation or the manufacturing part, low carbon emission or use light material. We just talk about the main details. But we are just going to talk about the make more durable furniture to increase lifespan and reusability. That's why that last one helps sustainable design. And there is a relationship between sustainability and reliability. And here I have a graph. So in Europe, 4% of the total urban waste is constituted furniture waste. It's inevitable. Every time we will have a waste. Estimated furniture waste at the state level varies between 2 to 19%, which is 5 to 20% of the urban waste. Urban waste. So, and also, if we increase awareness of the environmental impact of wood, so we can just call the furniture for reusability, remanufacturing, or recyclability. It's okay, we can do that. But still, recovery rate of the wood is still low, and it's because of the furniture waste. So wood is a biodegradable material. It takes 13 years for wood to be deteriorated in landfill. It takes 13 years. If we use surface application or finishes on the wood products, this time is increasing. Approximately 1/3 of the total amount of the furniture produced in the world is produced in European Union countries. Every year, more than 10 million pieces of furniture are thrown away by procedures and the customers in in Europe, in European Union, and anywhere in the world. So we have a vest. So this vest can be usable. And let's jump to human safety. The BIFMA and ANSI, the Furniture Sustainability Standard, says that injury rate of product must be reduced in its service. And also, European Commission says that a product cannot cause any danger for its user based on its nature of application. So legislation dictates that. So human safety must be considered in furniture production. So reliability must have direct impact on the safety issues of product in service. Therefore, if we decrease failure probability of the product, we can increase the chance of high reliability. So if we increase material strength or joint strength, and totally we can increase the construction strength. So that's why we can increase failure. We can increase reliability of the furniture. A company should make performance tests of their product to evaluate their product strength, durability, or stability or flammability. I'm talking about generally for strength and durability, but reliability based on the fire is important. So why is it important? Because company can prevent themselves product recalls and any possible danger in service. If a human get injured from the furniture accident, sometimes there are some examples of it. There were recalls for the furniture products. So it is really costly for the producers. And one of the largest causes for this recall is this design defect. This design defect generally comes from the liability. This defect results in manufacturing defects so that injury, accident, death, or simply failure rate in furniture service increases. I have a graph here. So this graph shows us how many people, what is the percentage of the people injured because of furniture. The children, infants, and seniors people, we have higher percentage because of the furniture accidents. In the adults, this percentage is low compared to television accidents or appliance accidents. This is from a report related to accident in the home, in house, in the living room or kitchen. So furniture, the accidents and injury rates because of the furniture is really high. So because of that, if we increase reliability, stability, strength of the furniture, we can decrease these numbers. We can provide more reliable furniture to users. And in here, I will talk about the market. So, but the title is different. So, title is gonna be related to competitive market. So, there is a relationship between reliability and operation cost. If we talk about the market, we need to check the cost. So, there is a relation between reliability and operation cost and elaboration cost. In the first time, this graphic shows us how our reliability in the x-axis and the cost is the y-axis. At the first time, if reliability low, our some costs is higher and low. In some part is getting together. But if we reliability increases, our CO is the operation cost. If reliability is higher, operation cost is lower. But the CT, it will be here, and CE and CD, CM manufacturing cost, design cost is increasing. If we are high reliability, if you want the high reliability, yes, the furniture producers should make investment for it, for design costs and the manufacturing costs. But later on that, in the long term, they will get its return. So by increasing reliability of furniture, we can increase chance of market success and cost investment. And in doing so, we can reduce probability of failure, carrying cost, warranty cost, service cost, and repair cost. So our actually manufacturing processes have knowledge about the reliability, so they can apply in their product. But actually, I would like to say that it's my observation. If there is no legislation which is dictated to furniture manufacturers, we cannot apply these standards or the legislation or the specification. For example, I will give a really quick example for that. For example, if we would like to buy a fiber board, MDF, or the particle board from the company to produce furniture, we choose that it should be E0 and E1 class because of the formaldehyde emission. Why we can do that? Why we are doing that? Because there is a legislation or standard in furniture product that class should be used, must be used, or has to be used. Because of that, we choose our panel products in this class. If we have standards, and these standards really dictated the furniture producers to have high reliable furniture, it will be easier to have more reliable products in service during the lifetime. So after that one, I will jump the fundamental probability theory. Before reliability analysis or probabilistic approach, we need to understand probability. What is the probability? We need to, let's look at it. So for this one, to understand probability, to set a probability, we need a variables. These variables we call random variables. Is one who is determined by outcome a random experiment. In here, we define capital X and lower X. While capital X denotes a random variable, X denotes a value of random variable in the experiment. It's a subset in our sample environment, sample space. For example, moment capacity of a double joints is a random variable in sample space. Other way, if we talk about the value of this moment capacity, like for example, moment capacity of double joints is 225 Newton meters. If we say that it's our value, it's lower X, we can define it that way. So random variable, we have two random variables. One is the discrete random variables, the other one continuous random variables. Let's look at what they are. The discrete random variables comes from countable values. For example, age, weight, height, and etc. And continuous random variables come from uncountable values. They are the material strength. That's why in engineering design, in probabilistic approach or predictive analysis, reliability analysis, we are using continuous random variables and its distributions. Let's make a case scenario. So we have a side chair frame like that. So in here we have a support in the tip of the front leg and the bottom of the rear leg, and we have two loads in here. The F1 and F2 is our random variables from an experiment. So what's our case scenario? A side frame of the chair is defined as shown in here. According to specification or standard, based on this standard or specification, we set this experiment configuration. Loads on a bunch of chairs. We apply the loads during testing. we apply load F1 and F2, and then so we get the result. So second chair, third chair, fourth chair, or 13th chair, 100 chair, how many we need, we can use samples. So we get the collected data. What is the load at tip of the rear leg, and what is the load at the middle of the side rail at the failure, for example. So based on the experimental results, mean of the F1 nioR is 2015 Newton. Here F1 2050 Newton, and the mean of the F2 is the 1000. For example, we have 20 samples, and mean of this 20 samples for F1 is the 2500, and F2 is the 1000. And their standard deviations are for F1 375 and for F2 125 Newton respectively. So what are the means and standard deviation for shear force and bending moment of joint on the side rail on the back post in here? So on the side rail and to back post and that joint, what is the shear force and bending force? For this one, we need one more information. What is the shear force and bending force as a function of F1 and F2? We can get it that functions for, with the regression analysis, or you can make a simple structure analysis. I did it at structure analysis. Based on the structure analysis, shear force and bending moment is given as a function of F1 and F2 below. And here and on this joint, shear force is equal to 1.7 F1 plus 0.56 F2. And moment is equal to 26 F2 minus 712 F1. So we need this data, this function to calculate our shear force and bending force. The solution comes from the joint probability density function. This function says us to find the mean of the shear force. The mean of the shear force, nioV, we define it. So we need to write same function in here. But instead of F1 and F2, we write nio1 and nio2. From question or case scenario, I know the nio1 and nio2. They are the mean of the F1 and F2. So if plot the nio1 and nio2 in here and make the calculation, I can find the mean for shear force on this joint. It is 5010 Newton. Let's move to how to find the standard deviation for shear force. It's a little bit more complicated, but it's getting easier in one point. So, according to joint probability density function, our equation will be here. This is the first part, is our standard deviation of the shear force, and we can use that equation. So in here, we need to know V and nioV. We know the V. V is equal to here. We can get the data from here, V. And also we know the nioV. We find it here. That's that one. We need to write it as a function of nio1 and nio2 here. So when I plug my values in here, my equation turns to this. So V equal to 1.78 F1 plus 0.565 F2, and same way UV in here. So I would like to put F1 and nio1 in the same parenthesis. I just changed the parameter. So next one here. So in here, I need to get the square of that data. Square of the first value, first value and second value multiply by 2, and the square of the second value. Because of the rule, it is this rule make our calculation easier. Here is getting 0. So my equation turns to here. I just out 1.78 square here. My equation turns that way. I have two equations. So if you look at the here, it is the same as here. If this equation equal to variation of the data set or square of the standard deviation, so that one is equal to sigma 1 square and sigma 2 square in this part. I will get it from here. So it's the same. So I know the sigma 1 and sigma 2 from the case scenario. And here I would like to draw your attention here. So if we get this one from that calculation and that rule, so I can directly write my equation, that one, the first one, this one, and eliminate all this one, and the second one, it should be like this. I can show my equation like in how to find the mean of the shear forces. So when I go to the calculate here, just plug my standard deviation from the question. So when I calculated, my standard deviation is 671 Newton. In the same way, we can calculate the mean and standard deviation for bending force. So we are using the same. So I will just make it quick, just this way. So I am using the same application. So for the mean of here is going to be bending force. I use that equation, and instead of F2 and F1, I plot to nioR and nioR and solve my equation. And my moment, average moment on that joint is going to be 1754 Newton meter clockwise. This is the negative moment. And the same way, I can calculate again here is going to be bending force, bending moment, standard deviation of bending moment. So I am just follow the same procedure. Because of the rule here is getting 0, so it makes my calculation easier. So that's why if I just go to the directly, I cannot see, but the standard deviation 267 Newton meter, the standard deviation. And that way, using joint probability density function and random variables, I can calculate means and standard deviation in any part of the furniture with these equations. So other way, I have to do that for every single sample. If I have 200 or 100 samples, I have to calculate one by one to find shear force and bending moment, and then I have to find their means and the standard deviations. This is the easiest one way to find the shear force or bending moment on joint or on material, any point of the member, we can find in this way. So also I will jump to next, multiple failure loads. For multiple failure modes, in here I will create a case scenario for a bookcase. In this one, we talk about the parallel system and the series system. So, and how we can use for this system when we calculate the reliability of the furniture construction itself. Let's start. In my case scenario, I define a bookcase in here. It has six corner joints, 1, 2, 3, 4, 5, and 6. In this case scenario, I have some assumption make easier my calculation. Yes, I will explain later this assumption. So in the second one, I just get every corner, L-shaped corner, and make them make a static loading test. And in here, I will distribute data from my L-shaped corner test in the capacity distribution. And if I get the data from this construction, and the data will be distributed in the load distribution and that part. And I will check the shaded area. What is the failure probability? So let's go to my case scenario. And here a bookcase is designed with the 6 corner joints and that one. So the joints are using 8mm dowels, 10mm dowels, or Minifix. We can use one of them or two of them. We will have different results in the next slide. We will see. And then, designer would like to set a random experiment with these 3 joint types and measure their bending moment capacity. So, I would like to measure their bending moment capacity with this experiment. So, this experiment is called diagonal tension test for L-shaped joints. So, I will make just one joint, apply the load from the tip, and get the results. So, in my experiment, the length of the members is the 30 millimeters. The length of we can see is the Z direction. Length of the members is 30 millimeters. I assume length of in Z direction, length of my bookcase is also 30 millimeters. It's gonna be same. Distance between doubles is 136 millimeters and end distance 82 millimeters. Same as the in joint and same as the in construction. And also distance between Minifix is 200 millimeters and end distance is the 50 meters. Both of them we have the same. In every corner, every joint, we have the same distances. So I make a test. So based on the results, I get this data. So I tested this L-shaped joint with the 8mm dowels, and my average bending moment capacity is 112, and standard deviation is 13, almost 13. If I use 10mm dowels in this L-shaped joint, average bending moment is 128, and standard deviation is 10 Newton meters. And lastly, if I use the Minifix in this joint and test them, my average bending moment capacity is 142 and the standard deviation 15 Newton meters. So I get my result, and for each joint type, every fasteners, I created my capacity distribution in here. So let's assume all corner joints in bookcase are diagonally withdrawn. So I apply the load. I assume that all joints is diagonally withdrawn. So in some cases there will be a compression, but because of making my calculation easier, I just assume one type of loading type. If my joint 3 under the compression, I have to get the result diagonal compression test. So, but to make it easier, I make this assumption. One point, I apply the load for same, but I just create a sample group for this construction. I apply the load. And I just get the test result. Means of the bending moment all corners is 94 Newton meter in construction, and the standard deviation 15.3 Newton meter. Let's assume it to make a calculation. So every joint has the same mean and the standard deviation. So how I can calculate the reliability single joint and the all construction? Let's see it. So if joint with 8 mm dowels, if I use only 8 mm dowels in the joint, what is the reliability of the construction? So for this one here, so here I just get the result from test joint sample, and I will get the result in here from my construction. If they are overlapped here, the failure will start. And if we go to the right side, failure probability is getting higher. So for this one, I just put in here, Q is my random variable. So let's see it. Q is random variable. The random variable related to strength of the 8 mm dowel in the joint and construction. So I am using that equation. So I know that this values in the former slide. So I give you from my test results. This is the mean of the 8 mm mean of the joint with 8 millimeters, and this is the construction 94. So I just calculate nu Q is 18 Newton meter. So I need to calculate standard deviation of this random variable. This random variable again pertains to this nu8 and nu8y. So for standard deviation, I need the square root of it and square of the nu8y plus square of the nu8. So I just plug my parameters from former slide. I will get the standard deviation for random variable 20.36 Newton meter. After that, what I do, I need to do z-test. I need to get z-score to determine failure probability. So for this z-test, we are using this equation, Q minus nu Q divided sigma Q. Q is 0 because I am just checking here if I just take a value and that point for nu8 is the same with the nu8y. So there is not any difference between them. That's why Q is always 0 and nu Q is 18. I find it, and sigma Q is the 20.62, and I calculate the z is minus 0.88. So for this one, I need to failure probability. For this one, I can use the z table from statistical book, or I can use MATLAB or R software to get my probability failure. For this one, we are using this equation. Probability failure equal to phi in parentheses z. If I use on MATLAB norm CDF parentheses that value, it gives me that failure probability. My failure probability is 0.1894. So my reliability 1 minus PF, it makes 0.8106. So 81.6% is reliability of one joint. So if I use the 8 mm dowels, my reliability will be for one joint 81%. So how we apply to it into the construction? So let's see the reliability of construction. For reliability construction, let's recall. Okay, in here we have some solution. Okay, let's recall that in reliability of construction, I am using series system. Series system, I have so I have the six corner joints. In six corner joints, they are linked to each other within series. So the joints are in the different corners. It means they are series system. So that's why I need to use this equation. RSS is the reliability of the series system. So in every corner joint, I found one of 81% is the reliability of one joint. 6 of them is the same result. They are the same joint based on my assumption. And then, so based on that equation, I need to multiply each reliability of the joint. So it makes 0.8116 power 6. And then my reliability is goes to 0.2838, and it makes 38.27% is the reliability of my construction with 8 mm dowel. Let's go to the 10 mm. I got 10 mm. I applying same procedure in here. So I'm just find the mean and standard deviation for random variables, and then I get the z-score for 10 mm dowels. Z-score is the minus 1.85. So I get the failure probability, and failure probability is 0.0322. It makes my joint reliability is 96.16. And then let's go to the reliability construction. Again, this system linked to each other in series system because the joint 1 has 10 mm dowels, joint 2 has 10 mm dowels, and everyone is the every corner joint is the pertains to here in one joint. So I just calculate my reliability of construction. I am using the same procedure again. So my reliability is getting higher compared to 8 millimeters. My reliability right now 79.06. If I use 10 millimeter dowel, my reliability is getting triple in the same construction. And if I go to the Minifix, if I use Minifix, what is the reliability of construction? I am just following the same procedure again here. So first, I need to find means and standard deviation of random variable, and from that values, I can find z value. Z value is the minus 2.19. So based on that z value, my failure probability, my probability of the one joint is getting higher, and it is 98.57. Again, in every corner joints, I use the same joints which I tested in the diagonal withdrawal joint test. So that's why it is linked to each other series system. So I am using the same equation again and follow the same procedure, and my reliability is 91.72. If I use Minifix, I get higher reliability in my furniture, in my construction, in my bookcase. But mostly Minifix are used with double joints. Let's try how we increase our reliability while using two joints. Let's see. Here, if joints with Minifix and 8 mm dowels are used, what is the probability of the construction? In one joint with the 8 mm dowel, my reliability is 81.06. and Minifix 98.57% my reliability. In series system, in here, I have my construction here again. So in parallel system, joint 1, I have 2 joints. One is Minifix, one is 8mm doubles. So that's why it is right now parallel system. Now every joint is in parallel system in itself. But when we look at the whole construction again, it's gonna be series system. First, I need to find reliability for one joint. If I use 8mm doubles and Minifix, and my reliability, my equation is here. So my reliability is I need to multiply 1 minus Minifix reliability multiply 1 minus 8mm doubles reliability, and then I need to subtract it from 1. So in here my equation set up. So my reliability in parallel system for one joint is getting higher 0.9973. So for one joint, I have this reliability level, 99% almost, 99.73. So when I go to the reliability of the construction, so I need to check, I just find the one of them, so I need to find all of them together. So that's why I need to use series system. And this 1 to 2 is linked to each other with series system. 2 to 4 is linked to each other with the series system. So that's why I need to use reliability equation for series system. And in one joint, I find the that value, and if I get its power of 6, so my reliability is getting higher, 98.40%. If I use Minifix and 8mm doubles. If I use Minifix and 10mm doubles, what is my reliability of construction? So here is my here is going to be 10mm double, reliability of the 10mm double, and reliability of the Minifix. So I will just use for the every joint. I need to calculate the its reliability. So I am using the parallel system again. So I am using the 10mm double reliability and Minifix reliability, and then I just calculate it. My reliability is getting higher if I use 10mm doubles. So basically and logically, it needs to get higher. My reliability in one joint is 0.9994. So I am using the series system to calculate the construction reliability. So, and every corner joint is equal reliability based on my assumption. So I am just calculating my reliability is 99.64% if I use Minifix and 10mm double. So in this way, we can calculate the reliability of the a construction or one joint with multiple failure modes. This is the one way to calculate reliability. Let's look at the another way. Let's jump the tolerance limits. Let's see what is the tolerance limits. Tolerance limits are, we just define a population. This population might be a chair. We get that population here. So, but we need to test this population. For this one, we need to get some samples. And this is my samples from my population. And I cannot test, cover all of my sample size. So I need the confidence level. So I just statistically test some percentage of my sample, and then I go to the future population. In here, what I am doing, in here sample test, I just tested my limits and just look what is the proportion level, what coverage level, and what percentage of the future population will be covered. In tolerance analysis, I am checking it. In confidence interval, I am checking only sample. In prediction interval, I am checking one value from population. This value can be any of them. But in tolerance analysis, I checked all this shaded area. So it is more powerful compared to confidence interval and the prediction interval. If you use a tolerance interval, it is more powerful. So this is definition, but we have some, what type of tolerance limits we have? Let's look at. We have two-side tolerance limits and one-side tolerance limits. And one-side tolerance limits, upper and lower tolerance limits. So in here, which tail, if we are interested, we name it. We are interested in one tail and the lower side. So that's why it is one-sided lower tolerance limit. If my data normal, I can calculate tolerance limit in this equation. So, but we don't need them. I will explain later, right now, because the software helps us. So, the one-side upper tolerance limits are related to acceptability of product characteristics. And otherwise, on the other hand, one-sided lower tolerance limits is determine reliability and safety of products. That's why we are using one-sided lower tolerance limits in our calculation to construct reliability. So, but before explain the calculation, we need to check some important points in tolerance analysis, because we have some assumption in tolerance limits. This assumption is randomness, homogeneity, and normality. So, in this assumption, we need the unbiased data. If we can this one, we can unbiased data. Our data should be normally distributed. During the testing or material selection, experiment, everything is in homogeneity, and in statistical way in experiment, we should choose random samples. So in here, if we unbiased data, we just met this assumption. We are using parametric tolerance analysis. If we cannot, it's gonna be non-parametric tolerance analysis. So after making the assumption, we can go which tolerance limits we can, which distribution we can use in tolerance analysis. So parametric tolerance analysis, we are using continuous distribution. So in random variables, it was the continuous random variables. Here again, we are going to continuous distribution. So if data normally distributed, we can use normal distribution. But sometimes we cannot have normal distribution in data set. In that time, we are looking for alternative methods for parametric tolerance analysis. They are the normalizing transformation. One easier way is the log normal data. We can distribute our data as log normal. And then after transformation, if data is not fit for normalizing transformation, we try the log normal data, but it's not fit my data. So I cannot use the log normal distribution. That's why I am using non-parametric tolerances. If my data doesn't fit any continuous distribution in here, normal distribution, Gaussian distribution, variable distribution, gamma distribution, log normal distribution, if it doesn't fit anyone, I need to use binomial probability, which is in this one, I am using the non-parametric tolerance analysis, and this non-parametric tolerance analysis is more conservative, because generally it gives us worst case scenario or lowest data in our data set. So that's why we just try to stay in this area to use this distribution. So tolerance limits. There is an article, I give the source here. For tolerance analysis, I am using the RStudio software. Is a free software. So this article explains every codes, R codes for tolerance analysis. It's a very useful source. So based on this source, I just modify the codes and get this data. And this is my chart for my testing. And this the red dashed line is my tolerance limits, lower tolerance limits. Also, I can see in the histogram that's the vertical red dashed line is my tolerance limits. In tolerance limits refers to, let's recall that here. That's one. Which one I choose? Or here, this is my capacity distribution at that point. If it is lower, that shaded area is getting narrower. If it is higher, shaded area is getting larger. So tolerance analysis help us to find that cross-section point. If we get a value, design value from that point, we can design our material or joint in the furniture construction. And let's go to the last one, predictive failure analysis, another sample of the reliability analysis. In this one, we are predict a life cycle or lifetime of a furniture construction. For this one, I create a case scenario. For this case scenario, I tested 30 samples. Here. This one is my chair. I just create a test experiment, and I am testing my chair construction and get their failure cycle or cycling level at failure. So for this one, what do I need? A chair frame and the performance test setup. I got the chair frame, and according to what type of standard I am using, I just set up my test configuration and start test. Cycles at failure for chair frame, an experiment. I try to front to back cycle load test in this one. It is just a simulation of the sit and up in real life. Cycle at failure for the chair frame. And I set up this one. And I need a distribution. For predictive failure analysis, I need to use variable distribution. What is the variable distribution? Variable distribution is best option to explain weak link phenomena. Generally used in probability of fatigue, failure of brittle material, and strength of the composite. So in here, we can use a plot. This plot is a QQ plot for variable distribution. I show you how to get this plot from our dataset on Excel. You can use Excel. You don't need to use any software or any statistical tool for this one. Excel is enough to find the life cycle of your product. And then what I will predict here. So I will predict lifetime or number of cycles. If reliability of the chair is 99.9%, it means I have only one failure in 1,000 products. Just one failure in 1,000 products. My reliability level show this one. I just give the reliability level for this one and measure its lifespan or lifetime or number of cycles. The second one, what is reliability? If the lifetime is given 200,000 cycles. And the third one, what is the reliability if lifetime is given 175,000 cycles? So let's check it. We have three questions. We will just create a data set and here. So this is my samples. I have 30 samples and this is my failure cycles. I just apply stepwise cycling loading method based on the American Library Association. So, but based on the specification or the standards, you can configure your test experiment. In here, based on the central limit theorem, I choose the 30 samples because I assume my data is normally distributed. Central limit theorem says that if sample size is 30, your data is normal. So you can safely make your statistical analysis. And here, I just give the my number, but I need to, my cycles, I need to sort from lowest to highest. Because variable distribution, I need to data from lowest to highest in the plot. So that's why I need to sort them on Excel. If you sort them, so in here, the lowest one, 177,668 cycles. This is my lowest value at the 24th samples. And I rank them 1. I just re-rank my numbers here because it is important for me. I rank them from 1 to 30 again. I renumbered the range from 1 to 30. And I calculate the failure rate. Failure rate is that if I have lower life cycle in my product in real life, if I applied that cycle, its failure rate is going to be lower. But if we apply the highest one, my failure rate will be higher. So that's why I need to calculate failure rate. How we can failure rate? The F is calculated as here as equal to n minus 0.5 divided n. In here, n is rank. If the rank 1, I plug the 1. And my total number, sample size, 30. So here, 1 minus 0.5 divided 30. So I will get that result. The second one. Second, minus 0.5 divided 30. And from the Excel equation, I get that failure rate from the Excel. So, and then I need to create my variable distribution. And this distribution, I need y-axis, axis, and x-axis. In here, x-axis. X-axis is the failure cycle of the natural log of the failure cycles. If I type equation here, ln in parentheses and that number, it will give me 12.08 blah blah blah. It will go this way. So if I just apply if I apply natural log every failure cycle, I will get that data set here. And then for y-axis, I need to use f and create that column. So for f, I apply that equation, natural log of 1 divided 1 minus f. I know f. If I make this calculation and then take its natural log and then take again natural log, I will get this data. If I type that equation into this cell, I will get minus 4.08. Y-axis and x-axis. Here, this is my variable distribution QQ plot for variable distribution, I will get this plot from these two columns. Y-axis is the light orange, x-axis is the light blue data. So first one, I will get that blue points first. I need to add thread line, R square and equation. That they are help us to create the liability calculation. So R square says that R square change 0 to 1. If close to 1, there are really minor errors. If it's getting away from 1, my error rate is increasing in statistical analysis. 88 is a good number, but not perfect. If we say R square is perfect, it should be around above the 95, maybe 99.95 or 99. So, and this equation is also good. I need to get this equation to calculate my lifetime or the failure cycle, because Y is related to failure rate here. Y-axis shows the failure rate, related to failure rate. And x-axis, x in this equation related to failure cycle. So I create that one. So let's go to the calculation, how to find lifespan or number of cycles or the reliability based on this plot. And here I just recall my plot again, and what I will predict. First one, what is lifetime or number of cycles if reliability of the chair is 99.99%? And here, so I need to find in the question the reliability level is given. If reliability level is 99.9, my failure rate F is equal to 0.001. Now the F, so I can calculate the Y in this equation. If I get the natural log of 1 divided 1 minus F, and this equation here, and Y equal to minus 6.9. And then I know Y, and from using this equation, I can calculate X. So I just write X. If I just keep along the X in this side and make the calculation, so my X is getting 11.8. So I know the X. What is the X? Natural log of failure cycle. So if I set up this equation, X equal to natural log of cycle, and X I find it 11.8 equal to natural log of cycle. So I need to find that value, and that value is transformed to here cycle. If I stay along the cycle here, and natural log goes to as denominator, so it's gonna be cycle equal to E over 11.86. So any scientific calculation or any calculation can calculate this value, and cycle goes to 142,486. So if I would like to set up a 99.9% reliability, my life cycle or lifetime should be that number. If it increases, my reliability level can be damaged. So second part, what is reliability if lifetime is given 200,000 cycles? In here, cycle is given and reliability is asked. So we just do reverse what we did in the first part. I know the cycle is 200,000. I just set up my equation for x equal to natural log of 200,000 and if I get the natural log of this value, x is getting 12.2. And then, if I know x, I can calculate the y because of that equation, which I get from my plot. So y equal to 16.7 multiply x minus 205.5, and y is minus 1.24. I know y, and then if I know y, I can find the f. F is failure rate, and in this one is a little bit longer because I took twice natural log of the value. So that's why if I just follow that equation, f is equal to 0.2508. It means that failure of the probability 25%. So reliability is 75%. If I give a life cycle, I define a life cycle 200,000 cycles, my reliability is 25%. Let's decrease this number. If we get 175,000 cycles is given, what is the reliability? And then I just follow the same procedure what I did here. So I just find the x 12.07 and y is the negative 3.4, and I can just follow I have to get twice natural log of the value, and the reliability is 96.96%. My reliability is really close to 1. If I just reduce 25,000 cycles in my lifespan or my lifetime or the cycles, my reliability is getting higher, almost more than 20%. So they are close to each other, but the reliability is the reliability gets much more higher than in this value. So I just create a table, and for just in table I gave the results in this tree calculation. That tree calculation, it is comes from that calculation. If we follow the same procedure, if my reliability equal to 6 sigma, it means I have only 4 failure in 1 million. My number of cycles, it should be 101,502. If my reliability is 0, I cannot give the 0 reliability because it cannot be calculated. That's why I just give the 0.01% reliability, and this one I have 235,981 cycles. If my product, my chair, or my furniture construction have 0 probability, and I need to reach that number. And also the last one gives us information about that. Carl Albert Ekman from Purdue University in one study say that if according to American Library Association, if a chair life cycle meets the light duty service load, the lifespan is around 6 to 7 years. In one paper it was mentioned. So based on this information, to reach the light duty service load according to American Library Association, I have to apply 150,000 cycles. So if just set up my lifetime or the number of cycles, based on that number, my reliability is 99.77%. So its opinion is we can just test his opinion, and based on this opinion, we get higher reliability. It is a good thing, and there is no any linear relationship between number of cycles and years, months, or days. Directly, we cannot say this day, this number. What we need to do for the say to give the lifetime as a day or year, our data should be a day, a number, a day, a year, or a month, or a week. Or if you would like to talk about the load, our data should be given Newton meter or moment or whatever it is. It should be given in this way. In this example, we gave our data in cycle. That's why we measured our lifetime as number of cycles, and based on that, we can create or we can set reliability of the construction, reliability of the product, or any product. And I say thank you. My presentation finish in here. If you have a question, I'm happy to answer them.